We present LeTac-MPC, a learning-based model predictive control for tactile-reactive grasping. Grasping is a reactive behavior for humans. We rely on our sense of touch to perceive the physical properties and state of the grasped object, and then dynamically adjust our finger movements. Our proposed LeTac-MPC enables robots to achieve the same effect in grasping as humans. We propose an MPC layer which combines prior knowledge of the system dynamics with data-driven models that are learned from tactile sensing. Our method combines the advantages of both data-driven and model-based methods. To collect the necessary data for training, we used 4 standardized blocks with different material properties. We developed an automatic data collection pipeline that recorded tactile images and gripper states under different grasping forces and external drag forces. Finally, we recorded the gripper positions when slipping occurs as labels. In the first task, the goal was to grasp various daily objects. When the object came into contact with the gripper width gradually converged. After this, the manipulator dynamically transported the object to the target location. For objects with rapid changes in acceleration and inertia, such as a box containing beads, the LeTac-MPC enabled the gripper to reactively regrasp the object to stabilize it in hand. Finally, the gripper width converged again. Although the tactile feedback for soft objects is subtle, LeTac-MPC can still converge and grasp them robustly. However, we observed that both MPC and PD controllers failed to converge, and the gripper motion could not track the reference generated by the grasping controller. This indicates the MPC and PD controllers continually decrease the gripper width until it reaches the force limit of the gripper. For open-loop grasping, because it cannot reactively grasp based on the feedback, it will destroy fragile objects like onion ring and drop objects during dynamic transportation. Our proposed LeTac-MPC demonstrated excellent generalization abilities. Despite being trained on a limited dataset consisting of only 4 standardized blocks, LeTac-MPC was able to successfully grasp various objects with different physical properties, sizes, shapes, and surface textures. Finally, we attempted to grasp a peeled boiled egg, which proved to be an extreme case and an ultimately unsuccessful experiment. The tactile feedback generated by the egg was so subtle that it was almost invisible, regardless of how much the gripper continued to contract. This resulted in incomplete convergence of the controller, causing the gripper to slowly contract at a very small speed. As the egg deformed and slipped in the gripper, the speed of contraction of the gripper increased, eventually leading to the destruction of the egg. However, the process lasted about 50 seconds. Therefore, LeTac-MPC worked to a certain extent for a peeled boiled egg. In the second experiment, we tested LeTac-MPC's reactive ability by shaking a box containing beads. During the shaking process, the box shook violently and its acceleration and inertia changed rapidly. However, LeTac-MPC adjusted the gripper width based on the tactile feedback and eventually converged, preventing the box from dropping. In contrast, open-loop control failed to handle the dynamic shaking, causing the box to be easily dropped due to the lack of reactive behavior. In the third experiment, we tested the effect of collisions on LeTac-MPC. We had the robot grasp a screwdriver and then collided with an obstacle, simulating an unexpected collision that can occur during some robot manipulation tasks. During the LeTac-MPC experiment, the screwdriver became loose in the hand due to the collision, causing the gripper to rapidly contract to regrasp the screwdriver. However, open-loop grasping could not handle this type of external impact, causing the grasped object to drop. Here is an experiment with a different obstacle. We can see the same result.